All right, so today we're going to go and look at the next section, which or section 8, that is, which is trinomial trees. And we started to talk about this last time, but just barely. So the trinomial tree is basically an extension, of course, of the binomial tree used for option pricing. And it took a while for this one to come out. The Cox-Rosser-Rubinstein paper came out in 1976, about 3 years after Black-Scholes. And here, though, it took about 10 years for Boyle to come up with this idea. He wasn't trying to explain, like, unlike Cox-Rosser and Rubinstein, who were basically trying to explain how the Black-Scholes model works. Boyle was basically suggesting that for certain types of options, it might make more sense to have a trinomial tree than a binomial tree because it adds more flexibility. And so for some very complicated cases like interest rate options, this might be the way to go. So the point of it was that even though it's more complicated and possibly more time consuming, it could pay for itself in the sense that it might be easier to model complicated options like interest rate options, or really any other options where we have to have the ability to make changes. For example, we may need to find or have the spacing of the time steps not be identical at every time step, or possibly we need the branches to stop rising at some point, or stop falling. And so this type of setup is a lot easier to make those changes to. So that was the motivation for this particular model. And it has a lot of advantages. You'll see that the coding is actually very straightforward because of the way the tree is structured. But of course, the drawback is that it will be more time consuming. Now, of course, in the 1980s, computer power was very limited compared to now. Computers are much, much slower. There's a lot less memory. And so at that point in time, efficiency was critically important in implementing these models. Whereas now, not that it's not important, but we're not so obsessed with trying to save as much space or time as possible. We really just want the best possible model because the computing power can basically overcome any inefficiencies. But anyway, what happens here is that we add a third tree. And for the first time, as you can see, instead of having a probability of going up and down, we also have a probability of staying at the same level. Now we're going to continue to use the same notation here. S is the starting value of the stock. Let's say we're pricing an equity option. And then if we go up, we reach SU. If we go down, we stay at SD. If we don't go anywhere, we'll just stay at S. Okay. Now, it doesn't have to work that way, but we'll start that way to keep it simple. For example, this middle branch could go down slightly or up slightly, but here, let's just say that it stays where it is. So now, of course, we have three probabilities, so we need three subscripts. We'll call them U, M, and D. And of course, they all have to add up to 1. So, oh yeah, as I started to say here, other optional tree structures or branching structures would be you could have two upward movements and one parallel or movement where you just stay where you are. Or down here at the other extreme, you could have the stock staying where it is or going down even further. Those are all possibilities. And even within the same tree, you can change the branching structure. It doesn't have to stay like this the whole way throughout. Although obviously it gets very complicated if you're going to try to switch these around. At least it's possible. And for some types of options, we do need this. As I started to say last time, the reason why this is so important with interest rate options is because unlike stocks, which have a long-term positive trend, and they can go up and up and up forever, interest rates don't behave that way. They may go up for a while, but they always eventually come back down again because when interest rates rise, it slows down the economy, and that eventually causes rates to start falling again. And then once rates are low enough, the economy starts waking up again, and then rates start to rise. So in the long run, interest rates tend to fluctuate over around a long run level. And this process, by the way, is referred to as mean reversion. And that simply means that the variable tends to return to the mean over time. Okay. So you definitely see this with interest rates. I'm not, off the top of my head, I'm not sure if there are any others that are obviously mean reverting, but there can be some. For example, commodities tend to follow the business cycle, and so their prices might also follow mean reversion. For example, if the economy is doing well, commodity prices would tend to rise. If the economy is slowing down, commodity prices would tend to fall as well due to reduced demand. So you can easily imagine that with commodities, we may run into something like this. Depends on the commodity. Anyway, so now here's my not so great effort to draw a tree with 3 branches. And of course, you can see it gets a little complicated. But the key here is that no matter what node we're at, we can all go up, stay where we are, or go down. And so the structure, while it looks terribly messy, it actually lends itself very nicely to implementing this as a matrix. I'll tell you why. One of the reasons for that is because unlike with the binomial tree, you can see that the branching structure is great, but it doesn't really lend itself well to storing this information in a matrix. Whereas with the trinomial tree, what you can do in principle is at the maturity date, you could create a matrix that has all of the terminal nodes and then use that same matrix for all the interior nodes because we can see how high or low it can go. And the beauty of this is that most of the nodes will be the same from one time step to the next. So within each time step, we don't have to change too much. Basically, all we're really doing is adding a maximum node and a minimum node, which are a little higher and lower than the existing ones. A lot of the interior of the tree is the same from one time step to the next. And that's not really true here. You'll see what I mean when we get to the coding. But yes, it's a very nice structure. It's very easy to replicate this with a matrix. All right, now what's different here though is that Cox, Ross, and Rubenstein chose the parameters of their model to replicate the Black-Scholes model, meaning that they want to make sure that the returns to the asset that the option is written on are normally distributed. Here, something like that is happening, but it's being based on this stochastic differential equation, which, by the way, is the one that Black-Scholes uses to replicate the behavior of the stock. They're assuming that the stock's price changes over the next instant in time by this small amount, ds, which follows this process. You can see there's 2 terms. The first one is what we call the deterministic drift, meaning that it has a trend, okay? And that trend is some constant. Not that it always goes up or down by that amount, but on average it does. Okay. The uncertainty comes from the second term, where we have the volatility parameter, and then the special term dz, which is itself another stochastic process called Brownian motion. So now this is what we're ultimately after. We're trying to model a stock price in such a way that while there's a lot of random ups and downs, those fluctuate around a long-term trend, which has a positive slope. Okay. You'll also notice the coefficient here, R minus Q. R is the risk-free rate of interest. Q is the yield of the underlying asset, if there is one, and both of these are continuously compounded. Then we have S, dt. The dt, by the way, represents an infinitesimal change in time. S is the current stock price, as that is the case here. And then the dz is the Brownian motion. So Brownian motion is its own separate stochastic process. And as we discussed last time, if you could imagine a random walk, which is a series of ups and downs, where on average, the process should be at 0. But as time elapses, we can move further and further away from the 0. It's like, and a good example of this is like, imagine if you were playing a game in a casino where, unlike a real casino, let's say there's a wheel being spun and 50% of the time it turns up one color and 50% the other color, let's say red and black. if you continue to bet on red all night in a game like that, sometimes you'll get lucky, you'll gain money, and other times you won't get so lucky. But on average, you should break even because there's a 50% chance of getting one color, 50% chance of the other. But having said that, within the first few spins of the wheel, you're going to be very, very close to the zero. As time elapses, if you keep playing, you could potentially get, let's say, a streak of 8 in a row that you win or lose. So you can get further and further away from the zero, but the longer you stay there, the more likely it is that you'll just break even. So the implication of this is that on average, this process is equal to zero, but the variance of this process increases linearly with the passage of time. I think these are summarized in here somewhere. Basically, the way to look at it is you could write it like this. Some constant parameter times t. And so then the square root, of course, standard deviation look like that. Now, this is a traditional random walk. It has no drift, or think of it as the drift is zero because the way the coin flip is set up, or the wheel in this case, let's say it's a wheel. And so the colors are equally likely to turn up. So if you keep betting on one of the colors, on average, you'll break even. But let's say instead, there's some game in the casino where on average you're winning money. It's hard to imagine that, but if that's what's happening, on average, you can see that the process bounces up and down, but on average, it's increasing. So we call that a random walk with positive trend. And then if like in the real world, you're playing a game like roulette where the odds are slightly against you, on average, you should expect to lose money. So the trend is negative, but the variance is still increasing over time. Okay, the amounts you can win or lose are growing as you keep playing the game. Now, Brownian motion is, imagine if you could spin the wheel an infinite number of times during the night, or there's an infinitesimally small amount of time between spins. Then you end up with this continuous process, which is called Brownian motion. This is going to be, by the way, the heart and soul of all these stochastic models that are used to price derivatives. So, anyway, so in practice, now, of course, you can't actually implement this in the computer the way it's written because these are, like I said, these are infinitesimally small changes. dt is an infinitesimally small change in time. dz is an infinitesimally small change in the value of the Brownian motion process. So what we have to do instead is use deltas, which means very small changes. And we end up with something like this. Okay, so there's a small change, a change in the stock price comes from the following two terms: the drift, and you notice here our old friend delta t, which is the size of a single time step, which can be very small, but it's not infinitesimal. And then what's interesting over here is dz, when it reduces to a discrete process, it's going to be expressed in the following way. This epsilon is a standard normal random variable. So now we're delving into the world of statistics. Now, of course, what that means is this is the normal curve, and then the standard normal distribution is the unique case where the mean is 0 and the standard deviation is 1. Okay. It's if you look at any statistics textbook, there's going to be tables in the back letting us calculate normal probabilities, those are all based on the standard normal distribution. This is a common distribution to use for calculating probabilities because it's very convenient. And so this is what it looks like. Okay, so epsilon follows this distribution. So what happens is at every time step, you have to visualize that we're randomly picking a number from this standard normal distribution. So for example, at time 1, epsilon 1 might be this. Time 2, the next epsilon could be maybe here. So in other words, it's like you have to visualize that what's happening is that we're randomly choosing from the standard normal distribution to come up with these values for epsilon. And each one of them is scaled by the square root of delta t. Okay, that way, the process has the correct statistical properties. Now, sometimes what happens is these trees, since they can be very unwieldy, it's not uncommon to use not the stock itself, but sometimes we see the log of S being used in its place. Sometimes that can help simplify the formulas. So here we're going to see what would happen if we, instead of modeling S directly, we model X, which is simply the natural log of S. And again, this is being done for efficiency reasons, which when this model came out, remember 1986, this was critically important because you can imagine implementing one of these trees was probably going to be very time consuming. And so they were going to come up with all the ways they could to make this as efficient as possible. Now, sometimes though, that makes it harder to visualize what's happening. But in this case, what they want you to see is that instead of what we had before, we're going to have X, which if you go up, goes up to X plus delta X, stays at X, or goes down to X minus delta X. Okay. Now, we still have the correct properties. Now, this is the way that the Hull's book shows the stochastic process followed by X as opposed to S. So this is the so-called drift of the process. And this is the volatility. Dx itself is an incremental change in the value of the log of S. So you've still got a deterministic drift, and you still have an uncertainty term here, but it's based on logs rather than the actual original values of S. Let's see. So then now this part is here. This is in Hull's book, he introduces this concept called the Ito's lemma. I think, let's see, do we have in the book, he's got the Ito's lemma based on S. This is the corresponding version for X. This, remember, we mentioned the Japanese mathematician Ito. He came up with a way of integrating random variables, and he called the whole thing the Ito. Well, actually, he called it stochastic calculus. Other people have since called it Ito's calculus, but this is the result that he came up with. And you can see there's a lot of partial derivatives in here. So, because remember, X itself is a function of the underlying asset in T. And so you can see we need partial derivatives because X is a function of two variables. And so that's why we have all these partial derivatives. And by the way, you'll see later on that these also all correspond to some of the Greeks, the risk measures that we've seen for options. For example, this is delta, this is theta, and this is gamma. We did this in the last semester, but I just want to mention that as we go along. And so this is the result. Now, the reason why this matters is because this is what we have to replicate on the tree. We have to make sure that this is the process being followed by dx. Now, what he's doing here is saying, well, listen, since we are choosing x to represent log of s, this, by the way, this process could apply to any x. But here in our specific case, we've chosen log of s, and that simplifies things quite a bit because clearly the first derivative of log s is 1 over s. The derivative with respect to t is 0 because it's not a function of t, but the second derivative is negative 1 over s squared. So we can do some substituting here and simplify things quite a bit. And by the way, this is where this falls out. Except keep in mind this Greek letter nu is just a shorthand for drift term of dx. And so we're going to write it like this, with the understanding that nu stands for this set of constants. Okay, it just makes it simpler to write it out, but you'll see in the code that in the beginning we're going to define nu as this drift term. And so now the discrete time version of this, it's exactly what you would have expected based on what we saw earlier. And this is what would get implemented on the tree if you choose to follow the log of x. By the way, if you do choose to follow the log of x, at the end you have to convert it back. Like because you're going to wind up with something like this. The call price is, let's say, natural log of 2.7 or whatever. So you have to figure out what the actual price is. Something, by taking the exponential of it. So when you do it this way, you're going to wind up with the log price of the option, not the actual price. So we have to convert it back at the end of the tree. So remember the dz in discrete time. And by the way, discrete simply means not continuous, or we don't have an infinite number of time steps this time. So this is what we mean by dz in discrete time. And then the d's become deltas, okay? All right, so now, with all that being said, now this is what they're gonna do. They're gonna say, listen, the tree needs to replicate this model. This is the log normal version of Black-Scholes, okay? So what they're gonna do is say, listen, how do we come up with 3 probabilities for our tree? Well, that means we have to solve 3 simultaneous equations. How do we do that? Well, we're going to make sure that whatever we pick, the expected value of those 3 branches is the new dt or new delta t. Okay. Oh, by the way, one more thing. Don't forget, since epsilon is a standard normal, random variable, that implies that the expected value is 0. So the variance should be delta t, and then the standard deviation should be this. Okay. So what they want us to do is make sure this is correct. So that means that if I apply expectations to this entire process, that means we're going to get this is going to zero, and this will be our expected value. So we have to make sure that the branches themselves provide us with an expected value at every time step of new dt or new delta t. Then they're going to do the same thing. And of course, this is the expected value. This is what it looks like. Because remember, PU brings us up by delta x. PM keeps us where we are with no change. PD brings us down by delta x. Now, then they're going to go through and prove what the variance needs to be. And anyway, and then we're going to require that these add up to 1. So the bottom line is these are the three formulas we're going to use. Okay, and here they are. We don't have to necessarily go through all the steps right now, but the one thing I do want to point out though is that the delta x itself, the size of the upward and downward movement, there's a lot of values it could assume, but Boyle in his paper tells us that he found that choosing sigma times radical 3 delta t seems to give us the most consistent results, the most accurate, consistent results. There's no theoretical reason to choose this one, but he finds from his research that this seems to work the best. Okay. Unlike Cox, Ross, and Rubinstein, they chose this U and D, but they also, said, listen, this is not the only approach that could be taken. We just find that it works well. And so the same thing is happening here. And you'll see when we get to the code that, this will figure prominently. Now, so yeah, what are we after? We know that if we keep increasing the number of time steps, we're hoping that it'll replicate the Black-Scholes model pretty quickly. And so Boyle found that if we used this value, it works very well. The number of time steps, that's up to us, okay? So anyway, at the end, you'll have an option price, which is actually based on the log. And then we have to work it out by taking the exponential, and we'll have our result. Okay, so with all that background, why don't we look at the code for a minute? Now, I've put it in here on a Word document so we can read it properly. And, it starts out as a subroutine or macro. But we have to watch out for the indexes. With a binomial tree, 0. And by the way, let's just quickly take a step back here. We remind ourselves that we have two indexes, I and j. I is time. J is the level reached by the asset price. But if you remember, with the binomial model, at the bottom branch, j was equal to 0. Okay, in fact, let me just make some space here so we can draw another example of this. So the indexes work like this. I is time, j is level. So here, for example, this node was designated 2, 0, 2, 1, 2, 2. The first indicates the time. The second one is the level, meaning from the bottom branch. This one would have been 1, 1, 1, 0, and then 0, 0. Okay, so interpret this 0 down here to mean the stock has not risen ever. Up here, it means the stock has risen twice. And then here it means the stock has risen once, which means that, of course, it's also fallen once. So what's going to be different now? And this is just for, you know, just because it seems to be more efficient this way. When you have a trinomial tree, it's more common to do this. I should be able to draw this properly with just two steps. So what's going to happen now is that we're going to let the center be j equals 0. So that means that this is j equals -1 and this is j equals -2. Now the time steps haven't changed. But all of a sudden we have negatives. Negative, if you see a -2, it means we've gone down from the center 2 steps. Okay. So in other words, now the center is 0. And the j's represent how far are we above or below the center. So we're interpreting it a little bit differently. Now, fortunately for us, VBA does have negative indices. A lot of programming languages do not. So this approach might not be possible in another language. Not that it's absolutely necessary, but this is how at least Boyle's model is usually implemented. So that's something we have to get used to. Okay, what else do we need to know? So again, what are we putting on this tree? X plus delta x minus delta x. And that implies, you can see how nicely this is going to work. Oh, well, that's just 2. And that's, of course, because we know that the product of one of the most famous properties of logarithms, the log of a product is equal to the sum of the logs. That's why it's working out this way. And you can see this will make it much easier for us to program it. Now, also, this time around, we're going to represent the stock tree and the option tree as a full matrix, 2 dimensions, I mean. Last time, remember, we only needed to keep track of one column at a time. Now we're going to have to keep the whole thing. So if you notice, we're going to represent the options with this matrix, or although again, it's called an array in VBA, a 2-dimensional array, with the indexes I and J. So basically what we're going to do is figure out the maximum number of time steps based on I. So here, for example, if this is a 2-period model, we're going to need 5 rows and 3 columns. Okay. So we're going to fill up the tree. And so we'll know from, so these are the I's, these are the J's. So for example, this will be x minus 2 delta x minus delta x. And but you notice, oh, now look how simple this is. So yeah, look how straightforward that is. This, and when you reach the same level, no matter what time you're at, you're going to have the same value in there. So this will be used to represent the log of the stock price. And then we'll do the same thing for the option. All right, now these parameters haven't changed. We need the same, okay, the only new constant, well, actually, this term, there's no Greek letters in here, of course, so we'll just use the letter V. That is our risk neutral drift of the logarithm. So in other words, as we saw in the slides, this is equal to this term, R minus Q, and we'll see it being defined later on in the code. Okay, now, of course, these two, changed. Dx, yes, okay. Now we're going to need this multiplier. Delta x is a constant. As you saw, we've decided that delta x equals sigma radical 3 delta t. But within a logarithm model, we're going to need to multiply to get up and down. We're going to need this term e to the delta x. And then, of course, we'll have the three formulas I just showed you for PU, PM, and PD. With the same indices. We have to tell it that we're going to introduce a matrix or an array rather for the asset price of the stock in this case and the call price. And by the way, this code is written for a European call. So that we saw earlier. At some point, we have to do a redim statement to tell it what the dimensions are. And then we're going to fill it up, of course. Now, these are all the constants. We need to use the dim statement, or we should. This is not mandatory, but it's a good idea to have a list in the beginning of all the variables that you're planning on using, or constants for that matter. And so you can see most of them are held over from the last time. The only ones that are new are these. Okay. Now, of course, we're going to, just like last time, we're going to tell it where to find these numbers. Let's look at our code, the actual spreadsheet. And by the way, interestingly enough, this is the same example we had last time. Look how far off it is compared to, remember the Black-Scholes price was $9 and 40 something cents. So what we might discover here is that if we keep increasing this, let's say to 100, it should get progressively closer to the true value, which if I remember correctly, was like 913 or whatever. We can go look it up, but this is the same example we had last time. So with 3, it starts out with not a very good accurate result. But then if we keep increasing n, of course, that'll continuously improve. Now, these are the parameters of the problem that we have to calculate. So here we are. So dt is just t over n, disk e to the minus r dt. This, as you just saw a minute ago, is this drift term. Let's sneak it in here. And then, of course, this is what we were talking about earlier. Dx is simply the vol. Here it is. Let's grab this. Now, of course, here, I mean, even though it says dx, it actually refers to delta x. Okay. And then, yeah, e to the dx. it's written as EDX, but it actually means that. Now, these, if you want, we can go back and double check, but these are the formulas we had in the slides. We need PU, PM, PD. And you can see we had a list here somewhere where all three of them are listed. Based on that moment matching process, where we have to make sure that the expected value of these three branches is 0. Wait a minute, where's that? Oh, not 0. The expected value is the drift term. Okay. The new dt, new delta t. That's right. The expected value has to be that. And the variance would be this. And then the standard deviation would be the square root of that. And then you have to add up to 1. Okay. So these are just these. Where are they? Right. You can see it's just these three formulas. All right. Now, with all that in place, the rest. Oh, and yes, redim. Now, here's the interesting part too. If you notice, when we redim it, we're giving it the actual dimensions. Capital N is the number of time steps. So we're going to create this as a square matrix of dimensions n by n, but well, actually, it's not n by n. It's n. Hold on. Let's go back and look at our graph again. If you notice, when we have 3 time steps, it's not a square, but there's still a regular structure to it. So what they're going to have us do to make sure there's enough room is think of it as negative n up to positive n in both dimensions if we need them. Now, you can see here the stock itself only needs 1 dimension because they're not going to change. It's the option tree that does need to be a full matrix, both rows and columns. So if we have 3 time steps, that means that the dimensions will be -3 up to +3. So we're allowing for the tree can have okay that many rows, those rows and those columns. Okay. Let's see. Let's go look at that one more time. Now, by the way, the reason for doing this, it appears like we've got way too many dimensions. No, this builds up to another technique that we're not going to actually use here, called finite difference methods, where you take a trinomial tree and you extend it to a full grid, and you would actually need all those extra nodes. We're not really going to need that here, but we're not going to change the code because it does work. But that's the reason why the dimensions seem to be so large, because finite difference methods, you're moving around in a grid, and the limit of the grid is going to replicate the trinomial tree, but it needs a lot more space. So that's why it's set up like this. So you can easily turn it into a finite difference method model, but we're not going to actually do that. We're going to skip ahead to Monte Carlo simulation, but that's one of the motivations for having such a large matrix. But we do need the negative indexes, okay? So, not all the space is going to waste. But that's the reason why it seems like it's a little bit overkill. But it's not. Okay. They're trying to kill two birds with one stone here. Anyway, so now of course we have to figure out how to fill in the two matrices. So let's say again, we'll keep it at n equals 3. And so S of negative 3, now we know already that it's supposed to be um, minus 3 delta x, but before we convert it to a log, it would actually look like this. Because if you take the log here, this is what we were calling x. Now this reduces to this. Okay, so we're going to start by filling in the tree with the actual values of s. And so that's why it's written like this, e to the n negative n dx. Now, how do we get from here to here? Well, the ratio of them is okay, so there's to go from here to here, you're multiplying by e to the delta x. Okay, so in other words, if j is negative 2, uh, this is negative 3, so you're getting your negative 3. Remember, e dx means e to the dx, delta x. So you can fill in the whole thing. You won't need to ever touch this thing again, okay? Because you filled out the maximum number of rows that we'll ever need. The rest of the tree in the earlier nodes will have blanks in the top and the bottom because like after 2 time steps, we haven't had time to go all the way up to E3 delta X or down to negative 3 delta X. So if you can imagine if we needed or wanted to fill in the rest of it, like if, let's say we did for some strange reason, you'd end up with and so in other words, you would just be missing the top and the bottom. And then one step earlier, you'd be missing the next two. So this is a good representation of the entire stock tree. Okay, it's like basically the terminal time step. We don't need to fill in the rest of it. But okay, now of course, what we normally do next is we'll do the same thing for the option tree at the maturity date or the terminal date. We'll just fill in all the intrinsic values or payoffs, as you can see. But then what's going to be different than what we're used to seeing is that, I don't know, let's see if we can draw a picture of this real fast. Remember, this one has three branches. So let's say here's your FU. Oh, you know what that reminds me? We have to we can't continue to use the same notation here because we've got three possibilities. So let's think of this as UM, UM, and UD. And so what's going to happen is just like every time we've done this in the past, this is a European option. Um, this would be equal to, oops. Okay, because now we got three possibilities. Here's P U, P M, P D. So this is the expected value of the option in one time step. And this is, of course, the discount factor. This is taking place one period in the future, so we need the present value. So you can see the loop. Once we've finished filling in the intrinsic or payoffs, intrinsic values or payoffs, all the interior nodes will do what you're seeing here. And so if you notice, it's kind of interesting the way it's written because wherever we are, IJ, the time step here will be one period in the future, so that'll automatically be I plus one. And then the J's will have to be J plus one, meaning you went up further, J itself, which means you stayed where you were, J minus one, which means you went down. Of course, the corresponding probabilities are PU, PM, and PD. And so this is how we fill in the rest. The loop, if you notice, it's going backwards from the future to the present. It stops at zero, which is today. It starts at n minus one because n itself is where all the payoffs are. Works its way backwards. You notice how we also need a next statement for each of these for loops. And within each time step, let's say we're time step 3. Oh, let's go look at the actual picture we had up here. The range of possible values, like here, I equals 3. Hold on. In order to fill in this column, I is 3, but we have 1, 2, 3, 4, 5, 6, 7 entries because we're going from 3 to negative 3, basically. Okay, altogether 7 entries, and so that's why this loop is listed as negative I to positive I. Okay. And at the end, when you're done, you just fill in the result. Now, of course, this is how we did it with the binomial option pricing model. So you're looking at this thing and saying, well, there's no way it can be this simple, but it is. Okay, the trick, I mean, the complicated part is figuring out what to do about those probabilities. The rest is very straightforward. So this in a nutshell is the trinomial option pricing model. And so again, you can see that the flexibility comes from the fact that the branching structure doesn't always have to be up, across, and down. You can put in somewhere in here a command which basically says, if you've reached a certain level on the top, change the branching structure to, let's say, this kind of thing. Or if you're in the bottom, you can change this. And the whole idea here is you may be in a position where you don't want this asset price to go too high or too low. So within the same tree, you can still switch. Here, we don't have that. It's just going through the whole thing, okay? But it would be easy to add that to the code if there's a good reason for it. Now, Supposedly, this is something we could adjust the time steps to if there's a need for it, but I don't think we want to get involved with that because it's going to be horribly messy. But now, by the way, what about puts? Well, we would only change the payoffs at maturity. Literally, the only difference between the put code and the call code, as we've seen before, because it's European, right here. Now, this model, though, will get very interesting when we switch to the American version, American calls and American puts, because now we have to make early exercise decisions throughout the entire tree. But the basic logic isn't any different than what we saw with the binomial option pricing model, meaning that if you do exercise early, you're going to collect the payoff. You lose all the time value, but you collect the payoff. So every one of these interior nodes, at every one of these nodes, we have to compare what we would get if it is not exercised early with what we would get if it is exercised early. And whichever is greater, that's what we put on the node. So we fill in the tree, and of course, at every step, we have to make sure that it doesn't make sense to exercise early. Now, it turns out, maybe we'll get back to this later on, but there's an interesting result in option pricing theory that I just want to mention right now while we're talking about this. It turns out, and I think we may have actually touched on this in one of our earlier sets of slides, that if an asset does not provide any cash flows to the owner, like for example, a non-dividend stock, it can be shown that an American call will never be exercised early. Now, here's why, because exercising early gives the investor access to that cash flow. So in other words, if you have an option on the British pound, for example, you're not getting, you don't actually have the British pounds, and you're not therefore earning the British pound rate of interest. So if you exercise it early, you are losing the time value of the option, but you're gaining the ability to earn the British pound rate of interest. So there's a trade-off there. You're getting something and you're losing something. But if there's no underlying cash flow, then exercising early just means you're giving up the time value and you're getting nothing in exchange for that. Okay. Or at the very most, you get the opportunity to take the proceeds and invest them at the risk-free rate of interest for the rest of the lifetime of the option. So we can prove that that will never be enough to compensate you for losing the time value. And so that being the case, American calls written on these non-asset paying dividend stocks rather, it will never make sense to exercise it early. That being the case, the price of the American call will be the same as the European call. On the other hand, with a put, even if the asset does not provide any cash flows, there is always a chance that early exercise makes sense. And it has to do with the opportunity cost of not exercising and leaving the money, the option, sitting there when you could be exercising and using the proceeds to invest. But the bottom line is American calls, if there's no underlying cash flow, will always be worth the same as a European call, but this is never true with a put. So if you ran some examples, if you took these programs and you ran a bunch of simulations with them, you would never find a tree, no matter how many steps you have, where you're going to find a node where it makes sense to pay off or exercise the option if there's no underlying asset and if it's a call. Okay. So anyway, I thought I'd mention that here. Now, in this example, Q is equal to 0.03, so that's not going to be a problem. In other words, if you run this code again as an American call, you'll see that there will be a difference if we at least run it enough time steps. But if you turn this into 0, you'll find that there'll never be a difference. So now what needs to be done next is to show you how you would adjust this model. I mean, specifically with the code for early exercise. I mean, we know in general how it would work, but I'd like you to be able to see how it would be implemented with this model. And so we'll save that, I guess, for next time. But then we can go on to Monte Carlo, which is what I really find extremely interesting, because it's a very different approach. It's just simulations. We don't need any market prices. What we do need is assumptions about the behavior of the underlying asset. And in principle, it can be used to price horrifically complicated options, which we'll go over, like the so-called exotic options. But the trade-off is that it's much, much more time-consuming than these models. So, but as time goes by, and as computers get faster, we may see a time when most of this stuff is done with Monte Carlo. Okay. So anyway, so we'll stop here. Now, next time, what we'll do is we'll take a look at the American call code just to see how this early exercise is handled, and then we can move on to Monte Carlo. All right, I guess we'll stop there, and I'll see you next time.